I'm so glad to have interacted with a lot of you over the last 3 days here at RICE at this RCQM workshop, and to have a chance to tell you a little bit about some of the stuff that we've been doing in collaboration with Ming's group. Is there a way to get rid of this bottom ribbon here? I guess not. Okay, we'll deal with that. So in the next few minutes, what I'd like to tell you is a story, or rather 2 stories, of Kramer nodal lines in quantum materials. So you'll notice that this is a little bit of a departure from the main theme of this workshop, the flat bands, but not entirely removed from the bigger picture of that of quantum materials and topology and correlations. So here's another test here. Okay, this isn't working. No, okay, I'll do this. This isn't working either. Something's not, my computer froze. Okay. There we go. Sorry. Before I begin, I need to acknowledge the collaboration, or the primary players in this research. And the work that I'll be showing is primarily that of my student Yu Zhang and one of Ming's students, Yi Chen. And we've benefited greatly, of course, from interactions with Vicky Lau and his postdoc, Julian Gao at Hong Kong University. And the work is primarily supported by A4SR, but we've benefited from support from DOE, NSF, and the fellowship from Humboldt Foundation. All right, so let me flash the summary and perhaps the key message of what I'm going to try to tell you in the next few minutes, and that is a story of samarium aluminum silicon, where we believe to have unveiled the first experimental observation of Kramer-Weil nodal lines. And that story goes together with another one of large anomalous Hall effect in this particular system, both in its antiferromagnetic state and in the paramagnetic state. And so this will be a story of a non-ferromagnetic material where we see large anomalous Hall effect. One of the points that will be hopefully apparent in the discussion of these Kramer nodal lines is that they are close but not exactly at the Fermi surface. And so we will contrast that with some similar work in indium tantalum disulfide. In this case, the crystal structure is completely different. The material system is very different, but it has the ingredients or the structural symmetry that's required for the occurrence of Kramer nodal lines, and via transport and RPES measurements together with calculations, we're able to confirm the Kramer's nodal lines. And in this case, they seem to occur exactly at the Fermi surface. And as a bonus, what we revealed was superconductivity in this particular composition of indium tantalum disulfide. All right, so let's see. This is the outline of what I'll be talking about. So let me start with Kramer nodal lines in samarium aluminum silicon. Perhaps it's worth taking a step back to see where they fit in the big picture of topological materials. We've heard a lot in this workshop about topological materials where their properties can be tuned or changed depending on what symmetries are broken or not, depending on the quantum geometry, depending on the presence or lack of correlations, etc. And in addition to that, all of these properties and new states of matter that we predict or observe have consequences in the experimental or physical properties and functionalities of these materials. So this is my material synthesis pitch to motivate the need to search for new materials, new states of matter, and new phases in topological and new phase transitions. And this is where Kramer fermions and Kramer nodal lines fit in. They are a very new addition to the family of topological materials, or relatively new, where it has been predicted that in chiral structures, these Kramer's fermions should be always present, and that is a universal characteristic of non-magnetic chiral crystal structures. And the way it shows up is that because of the lack of non-inversion symmetry and no mirror or rotoinversion, when spin orbit coupling is added, the degenerate bands before the addition of spin orbit coupling are now split everywhere except at some very special points in the reciprocal space called time reversal invariant momenta points, these high symmetry points, X, S, Y, gamma, etc. So the way this Fermi surface looked like before was that all these bands were degenerate, and now the degenerate is lifted, but the Kramer-Weil points are pinned at this trim special points. This is the case in chiral structures. However, in achiral non-centrosymmetric crystal structures, where now you have a mirror symmetry, the spin orbit coupling actually produces doubly degenerate nodal lines that connect these trim points. And this is an illustration of such a Brun zone in a hexagonal Brun zone. And notice how at high symmetry gamma points or M points, the bands are degenerate, but away from the gamma point or M, etc., the bands are split in the presence of spin orbit coupling. So that's where we looked at a lot of the theoretical work from Vicky Lau. And in addition to what I just described, which was his prediction for these achiral materials and the occurrence of Kramers nodal lines in such families of compounds, he also predicted that you can tune these, for example, by breaking the mirror symmetry. One way to do that would be by applying strain. And you notice that the calculation shown here reveals that the bands splitting increases with increased strain everywhere except at the trim points. All right. Another prediction coming from the same group is that the Kramers nodal lines enforce two types of Fermi surfaces, one called spindle and another one called Ogdong that look like this. And if you take a cut across the Kramers nodal line in a spindle system, what you observe is a splitting similar to a Rashba band splitting shown here. Whereas in an Ogdong system, what you would see are Dirac-like fermions. So we're looking for those in real materials, and this would be a consequence of those particular nodal line, Kramer-Weil fermions in the measurements in a thin film. You can expect quantized optical conductivity, kind of like what's observed in graphene, whereas in bulk, you can expect linear optical conductivity. Samarium aluminum silicon family of compounds is one that we should be looking at for Kramer-Weil fermions because it has exactly a non-centrosymmetric achiral crystal structure. And a lot of work has already been done on this family of compounds before we started looking for Kramer-Weil fermions. Perhaps this list is by now incomplete since a lot of work is still ongoing. But notice the crystal structure where the rare earths are these red atoms here, and the aluminum silicon form triangular plaquettes that are parallel to the C-axis, and they're either in the AC or the BC plane. And so what we decided to do was to look at the magnetotransport and band structure from both ARPES measurements and theory to try to identify the presence of these Kramer-Weil fermions and Kramer nodal lines. And this is, like I said, the work of Yu Zheng and Yi Chen. And this is published in this paper over here. All right. This is the guidance from band structure calculations that tells us that we should expect Kramer-Weil nodal lines. Here's the band structure without spin orbit coupling. And notice what happens, and I'm going to go back and forth a couple of times so that you can focus on the gamma Z bands. And notice that with the application of spin orbit coupling, those bands between gamma Z remain degenerate, but away from gamma Z, they're splitting. And then there are these pinpoints at the trim points in this high symmetry reciprocal space points. So it is our task now to confirm experimentally if that's the case. And Ming and Yichen have done a wonderful job with ARPES measurements, both vacuum ultraviolet and soft X-ray ARPES. When taking cuts in the gamma sigma z, perpendicular to the gamma z direction that I showed earlier, you notice that these points shift with different energies. And maybe a little too faint in this showing, the pink lines here are calculations that exactly trace what ARPES observes as a function of energy. So exactly traces these Kramers nodal lines. Furthermore, we wanted to see what the Weyl fermions would look like, and what you would expect is something that is reflected in this pink plane over here. Notice that the samarium aluminum silicon is predicted to have about 56 Weyl fermions or Weyl points. And so in order to look at these Weyl points, Yichen and Ming have done ARPES, and the top row here shows bulk ARPES measurements together with the bulk calculations, and they trace or agree very well. And then the bottom row shows the surface calculation, which should give us some information about the evolution of the Weyl fermions as a function of in the reciprocal space in the Brouin zone. All right. We did quantum oscillation measurements, angular dependent quantum oscillation measurements, in trying to add to this already wonderful agreement between ARPES and calculations. Notice that we see the Shubnikov the Haas oscillations in samarium aluminum silicon with the field applied in this BC plane. And then the fast Fourier transforms of these quantum oscillations give us the frequency as a function of angle. And when we map that out with the calculations, what we find are these pockets, alpha and beta pockets, that correspond to Weyl 1, Weyl 2 points identified in this calculation. And what this tells us is that indeed those Weyl points, the ones identified both from ARPES and from quantum oscillations, are close to the Fermi surface. That's not the end of the story in samarium aluminum silicon in as far as the topological properties are concerned. So let me switch a little bit to talk about the large anomalous Hall effect that we observed in this system. And I should preface this by saying that samarium aluminum silicon, as I'll show, has an antiferromagnetic ground state. And we observe large anomalous Hall effect both in the antiferromagnetic and in the paramagnetic grounds, in the paramagnetic states. And the proposal that I'm going to put forth is that we need a new model compared to what existed up to this point to explain the large anomalous Hall effect in a system with this particular symmetry and with this magnetic order. And again, this is work of Yu Zhang and Yichen and my former research scientist, Ximing Li. And the model that I alluded to is illustrated here, and I'm going to detail it as we go through the discussion of the data in the relevant data in this compound. But perhaps we need to take a step back and see what models existed that did account for large anomalous Hall effect in other systems, particularly in centrosymmetric systems. It had been proposed that either a non-collinear spin configuration could produce an effective field that then is responsible for large anomalous Hall, and that's illustrated over here, or that magnetic field can split degenerate bands and then produce these Weyl nodes, which then are responsible for non-zero Berry curvature and in turn for the occurrence of anomalous Hall. All of this is true in centrosymmetric compounds, and here are some examples of centrosymmetric compounds where a large anomalous Hall effect has been observed. Ferromagnetic compounds are listed here, where you can expect that the anomalous Hall is proportional to the magnetization, to the spontaneous magnetization. or antiferromagnets where there is no end dependence, but where any one of these other scenarios could be at play. Samarium aluminum silicon is neither. It's not centrosymmetric and it's not a ferromagnet, so it doesn't fit in any one of these boxes. And so what we are proposing is that in the absence of magnetic field, there are these Weil nodes at the same position in the opposite momenta in reciprocal space. But with the application of the field, these Weil nodes move and they are no longer at opposite momenta such that non-zero Chern number regions occur, and they are the ones producing or responsible for large anomalous Hall. Perhaps now I need to convince you that samarium aluminum silicon follows this prediction. First, by showing you briefly that it does order antiferromagnetically. Both our data and others before us has confirmed that, although the magnetic structure is not the easiest to solve because of an incommensurate magnetic structure that's apparent, and because of, I understand, samarium's high absorption for neutrons. So what we know is that the magnetic order is antiferromagnetic, and it's possibly incommensurate magnetic order. Here's our measurements of the Hall data, showing large Hall in a temperature ranging from 1.8 all the way up to 100 Kelvin. And notice that the magnetic order happens below 11.5 Kelvin. And so the large Hall resistivity extends well beyond that. It's easier to notice that there is an anomalous Hall contribution if we look not at the resistivity, but the anomalous conductivity as plotted in these three panels here. After we subtract what is likely a normal contribution based on the two-band model, we're left with a maximum at low fields, higher intensity at lower temperatures, decreasing in intensity as we increase the temperature. But still, as you can see in the contour plot in this phase diagram, the intensity of this remnant or anomalous Hall contribution is large in the low temperature, low field regime, but it extends further almost all the way up to 100 Kelvin at least, even if not quite as intense as at these low fields or low temperatures. When we compare the anomalous Hall contribution in samarium aluminum silicon with most of the other topological systems which do show large anomalous Hall, here's the summary of what the anomalous conductivity looks like in most of these systems, with the samarium aluminum silicon shown in pink here. And what you notice is that this absolute values of the anomalous Hall in samarium aluminum silicon is comparable with that in most of these other systems, but the mechanism has to be distinct from either, for example, gadolinium, platinum bismuth, or manganese 3 germanium, where the magnetic structure is collinear and the crystal structure is centrosymmetric. We're dealing with, like I said, the non-centrosymmetric crystal structure in very large anomalous Hall. Notice the change of slope in this sigma XX dependence as we go from the paramagnetic state to the antiparamagnetic state. If I have another minute or two, I'm going to leave you with this story of samarium aluminum silicon. Probably we haven't explained everything there is to explain in the complex properties of this material. But let me contrast that with what we observed in indium tantalum disulfide, and I'm going to have to go very quickly because I'm running out of time. But the punchline is that we observe Kramers nodal lines, and in this case, we believe that they are exactly at the Fermi surface. So let me see how much of that I'm going to be able to show you. The same prediction that I mentioned before, and here's the crystal structure that justifies or that motivated us to look at this particular compound. Our first measurements showed very good metallic behavior, and not just metallic behavior, but the superconducting state occurring below about 1 Kelvin or 0.9 Kelvin. And we've confirmed that bulk superconductivity in collaboration with a former postdoc, Alana, who's now at UBC, and her student. They measured the magnetic susceptibility, and then we measured specific heat, and we confirmed that this is indeed bulk and not some minute phase. And then here's the first measurement we did, which is the Haas-van-Alphen measurements. And you notice that the Haas-van-Alphen measurements show strong quantum oscillations that then reveal two pockets, as shown here in the amplitude as a function of frequency. And the analysis of the amplitude dependence as a function of temperature gives us this small effective masses for both those pockets, suggesting possible linear crossing and topological fermions in this compound. Then we turn to magnetoresistance, where we again see very large magnetoresistance and quantum oscillations, not with as high an amplitude as we did in the Haas-van-Alphen. But then we turn to our wonderful ARPES colleagues, and they produce what they refer to almost fakely beautiful ARPES data. This is where we see the Kramers nodal lines and the splitting away from the trim points. And some of you perhaps have had the chance to look at Ichen's poster on this compound. So I guess I'm going to summarize by contrasting the stories of samarium aluminum silicon and indium tantalum disulfide. There's more to the story of indium tantalum disulfide, where I've only talked about this particular 112 composition. There's another composition that this intercalation produces, which is indium a half tantalum disulfide. Surprisingly, or maybe not, the crystal structure there is slightly different than that of 112. And the third related compound to this is lead tantalum diselenide. And perhaps a bigger picture about the Kramers nodal lines in this family of compounds can be painted by looking at all of those. But since I'm out of time, I'm happy to stop here and take questions. Thank you.
In the samarium aluminum silicon. So could there be actually a ferromagnetic component that give rise to the anomaly?
We have, I didn't show all of the measurements that we have, but we have magnetization as a function of field and yeah.
There's nothing left. I mean, but typically incommensurate, magnetic scattering can potentially give a component that's has a zero moment along a particular direction, which can potentially contributing,
So I know that Colin has done neutron measurements on this. And I think that one of the problems that they had was that there was some aluminum silicon site mixing, in addition to the fact that this is an incommensurate. So depending on how much site mixing you have, the structure actually changes from non-centrosymmetric to centrosymmetric. And so I don't know that they were convinced that their structure remained.
Does your crystal have a site mixing as well?
As far as I can tell, no. We did single crystal X-rays, and we can't see this site mixing.
Right. So he's not using your crystal?
No.
Okay.
No, this, yeah, he measured, yeah.
Very interesting. So I had a question about the for the animal Hall effect. Since you see that the longitudinal and the transverse, they are not constant. There is some dependence, linear dependence. This means that it cannot be intrinsic, right?
Well, if you look at if you looked at all the others and what.
For instance, for the cobalt, it's constant, so it's more like band structure.
Well, so you look at there's some even in this. So these are not firm delineations, but you see that even for the others, there's some dependence before it becomes constant. And if you looked at this, I don't know what these triangles are. I think there's zirconium, manganese, phosphorus. It never really plateaus. This is manganese 3 germanium. It never really plateaus.
Okay, so you think it's not skew scattering?
No, yeah.
Any other questions? No. Thank you for the very interesting talk. Like, I want to make sure I understand correctly. The first part you talk about the Kramers, this nodal line, for that it's for the magnetic material, but that refers to the high temperature phase.
Yes,
At the low temperature, you see anomalous hole. The anomalous hole is like a, you believe it's an AFM structure, then but you show at a high magnetic field case. I assume in high
Yes.
magnetic fields, you polarize it to
Yeah.
a FM.
we see large anomalous hole even in the paramagnetic state.
Okay, but then I misunderstood it because in one figure you substrate.
Okay, maybe
Yeah, it looks
we
like
went too
a
quickly,
high field.
but we do see it in both
like
it's large. Look, this goes from 1.8 all the way to 100, and the magnetic order is somewhere here, and it's still large.
Okay, get it.
And
Thanks.
if we look at the, this is what I wanted to say, and I didn't show a lot of the data that goes behind this contour plot over here, and perhaps it's hard to see, but there's a lighter shade of blue over here that corresponds to some remnant anomalous contribution, even at these high temperatures. That's why we're showing this more or less blank phase diagram here. There's a very important bit of information there.
What makes you confident that you have the right to take that curve as your background, saying that's the 2-band? I mean, you could go 3-band, 4-band, 5-band,
That's
whatever. Is there any particular reason that you think that your 2-band thing is capturing the band structure?
Can you imagine a way in which you add more and more bands and
Well, I mean-
will mimic? No, I'm just saying that at high fields, we fit it with this 2-band model. There's the best we can do. I'm not saying that this is the absolute description of what the conductivity is, but I don't know how I would capture this peak over here with any number of bands. That will also fit, I have to fit the high field data, right? So one firm constraint is that I have to be able to fit the high field data.
I cannot tell, sorry, yeah.
I don't know.
And also one more 100 Kelvin, 1-band, from the band or 2-band there, and they are also almost there. So he thinks that basically you can use this also to the lower temperature as an approximation.
It's not proof. I'm not claiming that I know for sure that that's the description. I'm just saying that it's reasonable based on the fact that we see the large contribution at high temperatures, and that I have to be able to fit the high field data with some calculation.